Okay, so today's topic is about non-ideal op-amp analysis. What does that mean? Is it op-amp analysis that you get wrong? Not quite ideal. Not quite. It's op-amp analysis where just to bring to light some of the things that happen when you start dealing with real op-amps. Okay, so far we've assumed in all of our analysis that the op-amps are ideal. You get no current going into the input terminals. And we have the open loop gain, which is that AOL parameter, being infinite. You've got zero output resistance, infinite input resistance, all those things. What happens if we relax those assumptions? And that's what we're going to look at today. Why is this important? Well, it's important because depending on the amount of money you spend on an op-amp, you get varying qualities of op-amp. Okay, so before we start that, just wanted to show you a great thing that was enabled by electrical engineering. I don't know if any of you will know it. It's very, very recent. Anyone seen this? Yeah? Put your hand up if you've got it. Okay, so not that many. Probably before a lot of your time, but this just came out yesterday. Whole load of fun. Happy to discuss. Yeah, and video games are a great thing enabled by electrical and computer systems engineering. Thank you very much. Okay. So, what you want to be able to do by the end of today is recall what are the three key things, what are the three key concepts of an ideal op-amp. And these are listed here. That there's infinite open loop gain. You hear that term again and again. It's an important one. There's infinite input impedance and zero output impedance. Okay? So these three things you need to remember is what an ideal op-amp is and what comes out of that. What are the consequences of this? And we want to show how negative feedback controls the gain of the overall amplifier system with a little bit of maths and the system put together. Okay, so recall that we saw this slide last week in the very first op-amp lecture, and it talked about a simple model of that really complicated model of the op-amp. And this was primarily to enable first and second year students to understand op-amps without blowing your mind away and turning you off electrical engineering. So we deal with the ideal op-amps, and now I'm just going to go back and look at the simple op-amps and what that means. So the key parameters here. The key things here are that we simplified this by making these three parameters ideal values: infinity on the input, zero on the output, and infinite open loop gain. And that made this our ideal model. Okay, all well and good. But, as Boromir always says, one does not simply use the ideal model for everything. We have to use the simple model to take into account some other considerations when designing circuits that use op-amps. Okay, so how can we compare? Let's do some analysis of the non-ideal op-amp with something really simple. And in this case, here was our most simple op-amp circuit, which was the unity gain buffer, right? So we took the output, connected it back to the negative input, and this put the op-amp into negative feedback. And with the ideal model, the overall gain was this, right? V out over Vs equals 1, and we can get that from Kirchhoff's current law and the negative feedback law. So what happens if we now get rid of this and use the simple model? Okay, so how do we do that? Okay, so let's take our circuit and substitute back in the simple model where the op-amp symbol is. So previously, we just had this nice triangle box. We didn't care what was inside it. Now let's have a look at what happens when we put these components inside it. Now bear in mind, this model itself is a simplification of the really, really complex model with 15 transistors in it. So even this is not exact, but it gets you close enough to understand the behavior of the op amp. Okay, so what do you do to analyze something like this? We want to find, again, V out over V in, or Vs in this case, the gain. And in the ideal case, the gain was equal to 1. What is the gain in this case? So how do we do that? What we do is what we do for pretty much everything in ENG1030. So we use Kirchhoff's current law. Okay? So what we can do is relate, just like we did using the op amp before, V out to Vs. And how do we do that? Well, you write a Kirchhoff's current law equation for a particular node. Okay, let's just say this is the node that we're looking at. Well, this red line all is really one node, right? So all the currents coming into or out of this node must sum to 0, and I've denoted those as I1 and I2. Okay, so we've got those here. And then we write equations for I1 and I2. So that's what we've got here. So I1 plus I2 must be equal to 0 because of Kirchhoff's current law. And also note here that V plus is connected to Vs, so they're the same. And V minus here is connected to V out, so they're the same as well. So that's why I've done some substitutions here. So here, I1 is equal to, now I1 is the voltage at this node going through the resistor Ri, right? So that would be equal to, all right, so the voltage V minus subtract V plus, which is really V out subtract Vs, divided by the resistance Ri. Can we see that? So that's I1 here. What's I2? Well, I2 is the current going the other way, and that would be the current here, and that flows all the way through here, through this resistor RO, right? So that's I2 there as well, because that's all one current. So what's that? That will be V out, that's node here, subtract the voltage at this node, which we get as AOL times Vs minus V out, right? Because this is V plus and V minus, so that's Vs and V out, divided by the resistance RO. Okay? All right, so after a slight bit of sleight of hand and manipulation, we can solve those two equations. I assure you, it's simple algebra, just with a few extra lines. So anyway, I've taken this, stuffed it in here, taken I2, stuffed it in there, and I've set that equal to 0. There's no magic here, direct substitution. So here's I1, here's I2, and the sum of those must be equal to 0, and you can work that all the way through. I can multiply through by Ri and Ro, take some V outs, factorize those out, and eventually I come out with this, and that becomes this. Okay, so this is the neatest that I managed to make V out over Vs. And the key thing here is that this is for the simple model. All right? And for the ideal model, what do we get for V out over Vs? 1, right? So now, hopefully, you can see that it's not, if we play around with these different parameters, you can get things which are not going to be 1. Okay? And this is not out of the realms of probability because, in fact, these these values, depending on the op-amp that you buy, they're going to range from close to ideal, which is high input impedance, low input impedance, whatever, to not so close to ideal. And in fact, also, this parameter here, which we assume is very large, actually tends to get smaller and smaller as we use the op-amp in a faster and faster electronics. Okay, so have a go at this just to see what we would get. Oops. There was an error selecting this question. That's interesting. Oh, my. So have a go at that. I'll open it up. Let's hope that was a one-off. Yep, so it's open now. So this is just to give you an idea of what happens when we start changing these values. I want you to calculate and use this equation to figure out what this V out over Vs is. Oh, and sorry, this is equal to G. Okay, so this is really just to test if you should be in this course or not. Because to get here you would have had to do some form of maths that involved algebra. There we go. We're back. All right, how are we all doing? Okay. Oh, anyone want to switch their answer? Right. I think it's pretty clear that everyone thinks it's 0.67. Is that right? Do we ask the audience? Because the audience got it wrong last time, I remember. No, that's right. The answer is rounded to 2 decimal places, 0.67. Okay, so even just by putting in some different values for Ri and Ro that could be realistic, you think, oh, how's this realistic? You couldn't get that at all, because I've been telling you that AOL is approximately equal to 100,000. Well, it turns out that if I plot this graph of AOL versus, so let's say this is 10 to the 5, this is 10 to the 0, versus a signal that goes into the op-amp with a frequency f, that this is what tends to happen to AOL over, something like that. Okay? So that's real. And if you look at the spec sheet, which is in the back of your lab manual, for the op-amp that you've got, the TL074, you'll find that this is in fact the case. Also, okay, so maybe these values aren't so realistic, but this one is. Okay, so according to the ideal model, the gain would be 1. And if you decide to design a circuit with an op-amp and you don't understand those parameters on the spec sheet, RI, RO, and AOL, you're probably going to design a wrong op-amp that won't work off paper. Okay, so what are the implications of this? Well, okay, so if RI is much greater than RO, so from this equation, if you assume this is the case, RI is much larger than RO, which is usually the case, then this drops out because that's much smaller than RI, and this sort of becomes 1 over AOL, and AOL becomes the key parameter. Okay, so make sure that whatever circuit you design, you take these into account. Otherwise, this may not always be true. Okay, so that's just looking at the op-amp in terms of how you use it in a circuit as a unity gain buffer. So that's showing that the gain doesn't always change. Oh, also the other implication of this thing, a very big implication, which I almost missed, is that this all comes about because of negative feedback. Okay, so someone asked last Wednesday, why do we care about negative feedback? And I replied, well, negative feedback makes V plus equal to V minus, right? Remember I said that? Well, I had no such assumption when I looked at this circuit, right? I didn't say that V plus had to equal V minus in this particular example. So I didn't say, because there's negative feedback, V plus equals V minus. It turns out that this V out being connected to V minus, in the case of the unity gain buffer, when I do analysis with a simple op-amp model, comes out to, gives me this equation, okay? And this equation will always be very close to 1 if AOL is large, okay? And in fact, even if AOL gets pretty small, even if AOL drops to like 1, then this gain is still approximately 0.5, right? So, in fact, what we've done is AOL can be a large range of numbers, and we will still get the overall gain of this circuit to be around 1. Okay, so AOL could be something from, say, even if I put it at 10, all the way up to 100,000, this will still hold true, right? Now, if I start putting a few resistors in there, and it's not a unity gain buffer, all the maths is exactly the same, and it will come out pretty much to the fact that AOL being large makes it so that we simplify everything by saying V plus equals V minus. Okay, so I've sort of given that to you a little bit backwards, but there was a reason for that, which is I wanted you to start using the op-amp before fully understanding what's going on. Okay, so this is why, well, negative feedback allows us to not be stuck with AOL as our gain factor. Okay, so what about this example? Okay, so now we've got this op-amp here, and we've got some source voltage and some load resistance. Okay, so how does a simple model affect connected sources and loads? Let's assume that this is connected to ground, and this is all ground. And note, there is not negative feedback in this circuit. Okay, there is no current that can flow from here all the way back this way. All current flows to ground. Okay, so this is a little bit tricky. It appears that there is, but there isn't. In fact, I could do away with all that and just say, look, this is not, let's get rid of this, and just say that these are connected to ground. I might update that for the next picture anyway. Sorry about that. Okay, so let's analyze this and see what happens. I won't go through the big analysis. It's exactly the same. You get a current this way, you get a current through this way, and you equate. And what you get after you skip all the gory details is now the gain V out over Vs is equal to this mess. Okay? Now this mess, interestingly enough, relies on all of the resistors. So you've got Ri plus Rs, RL over RO plus RL. And in the ideal model, if we assumed these values, right, then you can simplify all that to V out over Vs equals AOL. So in our ideal model, we had this, V plus, V minus, okay, AOL times V plus subtract V minus, right? So that was ideal. For our simple model, we now have these two factors to consider. Okay, so that's the effect of relaxing these two assumptions. Okay, so if Ri was infinite, then this would be pretty much, this would come out to 1. So if Ri is really large, this comes out to 1. And over here, RL over RO plus RL, well, if RO is 0, then this just becomes 1 as well, right? So you get V out over Vs is just equal to AOL. Okay, so what happens if we don't? So what happens if we now go to the case where this is not ideal? Well, here's an example. So I've just substituted a number of values in for Rs, Ri, Ro, and RL. I haven't got you to do it. I'll do it here. And the most interesting case is, let's say, okay, so these are some realistic values for the op amp. So this is the op amp. And this is a realistic value for the source resistance. And these are some possible values for the load resistance. Okay, so remember, you've got the op amp, you've got the source, and you've got some output here on a load. And I said that sources and loads can have different values of resistance, and so these are typical values for those resistances. Okay, so let's say for these values, your load resistance is just 4 ohms. Okay? So if I take those values and plug them into this equation, I get V out over Vs, so this is V out over Vs, is equal to something of the order of 2,600. Now, on the ideal model, we would get V out over Vs equals AOL. All right, equals 100,000. Considerable difference here. Okay, all because we're now using realistic values for the components that we're putting in our circuit. As we increase the value of the load resistance, so over here, we're increasing that value of load resistance that we're putting onto the op-amp, then our value of V out over Vs starts approaching the ideal value of AOL. Okay? And this is all because we're not using the ideal op-amp again. Okay, so for the vast majority of the stuff you do in ENG1030, it is sufficient to assume the ideal op-amp, but when you start getting into some more useful circuits, where you're putting together blocks of circuits, so this might be circuit 1, this might be circuit 1, this might be an op-amp, and this might be some circuit 2, and you start hooking them together, you need to start thinking about what resistance this side has and what resistance this side has, and put that in terms of the parameters of the op-amp. So if these match well, then you're going, the circuit's going to perform properly. If not, the circuit will have glitches. Okay? Finally, what is the effect of negative feedback in all of this? So I touched on it before, but just to make it explicit, so when you revise this, well, with the unity gain buffer as an example with negative feedback, it turns our gain equation into something which does not depend too much on the exact op-amp that you use. As long as the open loop gain of that op-amp is big, then our gain is fully defined by the components we put around it. Okay, so in this case, we have no components. We've just connected the negative feedback. That negative feedback makes it so that our gain is really stable and steady as opposed to fluctuating with this one parameter, this AOL parameter. Okay, so, and also now for an op-amp without feedback, the gain of the op-amp is totally dependent on AOL. And the problem with that is AOL varies really significantly between individual op-amps. Even if you swap in the same op-amp, because you broke your other one, you put in the same op-amp, AOL would be pretty much guaranteed to be different. So if you design for that, that's why we do not use op-amps often without negative feedback. Okay, so the overall gain summarized is much more controlled with negative feedback. Okay, so in summary, this is a short lecture, which is good. Okay, so in this simple model, there is some current flowing through the terminals, okay? So I minus is not exactly equal to 0, and I plus. Without negative feedback, so if we just use an op-amp like this, this gain will vary really, really undesirably with AOL. And finally, real values of the input and output resistance should be accounted for when you design your circuit. Okay.